So, okay. One second. Okay, so thank you very much, everyone, for being here. We welcome to this last seminar of the year organized by the Faculty of Science of Universidad Arturo Prat, which is placed in the north of Chile, in Iquique. Very nice place when we are not in pandemic time, but it's quite beautiful, I assure you. So this time the speaker will be Cristóbal Corral, a member of our team, who was actually leading the organization of this seminar during this year. So I will give a brief introduction about Cristóbal. So Cristóbal obtained his bachelor and doctorate degrees from the Universidad Técnica Federico Santa María of Valparaíso, under the guidance of Dr. Sergei Kovalenko, right? And well, the subject of his doctoral thesis was related with phenomenology and of particles in torsion spaces. So between 2015 and 2019, he carried out 3 postdocs. The first one at the same university he obtained his PhD. Then a second one in the Universidad Autónoma de Mexico, and a third one in Universidad de Santiago, USACH. And he's currently part of our team here at UNAD. He's an associate professor here. So during his career, Cristóbal has obtained various grants, projects, and awards, both national and international. And in particular, he obtained some recognition by CONACYT in Mexico as level 1 national researcher. So also it's worth to mention that he got this year another project, Fondesit initiation project, which are quite important here in Chile, and also for our group it was a reason of we were very happy for having this award, which for sure is also a positive thing for our group. So to the until now, he has published 14 papers with almost 700 citations. And between the research interest of Cristóbal, we find gravitation and cosmology, modified theories of gravity, exact solutions such as gravitational instantons, you said? Yeah, and black holes, black strings, and also he's interested in conserved charges and black hole thermodynamics. So as you can see, the title of this talk will be Topological Terms and the Misner String Entropy, which correspond to an article that he has just submitted with his collaborators just by the end of this November, it was, something like that?
Yeah.
So, well, the place is yours. So welcome, Cristóbal.
Thank you, Nelson, very much for the introduction. It is really a pleasure to be here in the last seminar of this year, and I would like to thank all the people which has been part of this seminar series. And since we are doing a stronger group in the north of Chile, so we are really happy about that. And today I have the pleasure to present this preprint, because it is not published yet. And it is named Topological Terms and Misner String Entropy. The archive number is down here, so if you have if you are interested in this, so you can go here. And this work was done in collaboration with Luca Ciambelli, who is a postdoc in the Free University of Brussels, with Jose Pablo Figueroa, who is a master student at University of Concepcion, with Gaston Guiribet, who is a professor in Universidad de Buenos Aires, and also with Rodrigo Lea, who is a professor in Universidad Andrés Bello in Chile. So I also have the pleasure, because all of them are here in the audience, so if you have any question and I am not allowed to answer properly, so they can give me a hand on this. The outline of this talk is first of all, I will give an introduction about the top nut and bolt geometry in ADS and how this object, which is the main interest of us in this work, arise. This is the Misner thing. I will spend some time motivating this geometry and telling you what are some details about it. After that, I will go to a brief review about the netherworld formalism in order to compute the conserved charges of this gravitational solution. And then we are going to see some drawbacks. In particular, in ADS, some of the charges will be infinite. So we need a renormalization prescription to make sense out of this. And this is done by introducing some topological terms. And this is the third part of the talk. And we will see how these topological terms render the Misner string entropy finite. And finally, I will present some conclusions and remark. So hopefully I will be brief. Okay, so let's go with the first part about top nut and bolts in ADS and the Misner. So I see, I heard a background noise. Okay, so now I don't. Okay, so the best theory of gravity that we have so far is the Einstein theory of general relativity. This theory can be formulated from an action principle, which is given here. This is the Einstein-Hilbert action. This theory is invariant under diffeomorphisms and also under local Lorentz transformations. And even though this theory doesn't account for some things like the nature of the accelerated expansion of the universe and doesn't explain the entropy of black holes in terms of microstates, is the best theory of gravity that we have so far, and it is, as an effective description, is the best that we have. So this is a theory for the space-time itself, and if you would like to have the field equations, you have to perform stationary variations of this action with respect to the metric. And in this sense, you get the Einstein field equations, which are written down here, and they have I included the cosmological constant from the scratch, even though this wasn't included at the beginning of the formulation. So there is a huge enterprise in solving the Einstein field equations, and perhaps the most well-known solution is the Schwarzschild black hole. But during the 20s, the people also was interested in solving these equations in a cosmological setup by assuming an isotropic and homogeneous spacetime. And this was also interesting, and other kind of solutions were shown. And later on, during the 50s, there was the first attempt to generalize the Schwarzschild metric. And this attempt was done by Taub in this article down here, and also by Neumann, Tamburino, and Unti. And this was the first attempt to get a stationary metric, including rotation. And this is the metric. This is the solution to the Einstein field equations in presence of the cosmological constant. The metric function f that solves this equation is given down here. And from now on, I will assume that the lambda is related to the ADS radius through these equations. Through these equations, sorry. There are some things that I can mention about this metric. The first thing, if you take a look to the area coordinate here, the area coordinate is actually, it doesn't vanish for any value of the radial coordinate r. So this space can be extended for all values of r, And in fact, if you compute the curvature invariants out of this metric, they are all regular for all values of R. And indeed, this solution is connected smoothly to Schwarzschild ADS in the limit when you take this parameter n going to 0. And from now on, this parameter n will be regarded as the NAT charge. Okay, this is an extension of the Schwarzschild ADS metric, and in the limit of n going to 0 reduces to Schwarzschild ADS. To the best of my knowledge, the introduction of the cosmological constant into this solution, the tau NAT and Bolt solution, was done by Hawking and Hunter and Page during the 90s. So if I am wrong, please feel free to comment about it. But the first solutions by Taub and Neumann, Tamburino, and Unti, the cosmological constant was absent. What about the symmetries of this metric? Actually, the symmetry is locally SU2 times R. There is a super nice review about the symmetries of this solution in this archive number, which is down here, and Rob League and Pet2 are here in the audience. So I am glad that you are here, guys. And they have a super nice review of the symmetries of tau NAT in this appendix. And as I was saying, the symmetries of this solution is locally SU2 times R, where R refers to this generator. This is the time generator in this case. And the interesting thing is that the NAT charge introduces the time generator into the SU2 ones. Nevertheless, this locally looks like SU2 times R, but there are some interesting global properties that I am going to show you in a few moments. So there is another way to see tau NAT, and actually, if you have a line element in the following form, which is actually the form of tau NAT, you can see here that this sort of vector potential, if I can go back here, that is proportional to the NAT charge. In this case, if you start throwing particles following geodesics, usually there appears an electric part, which in gravitation is analogous to the Newtonian potential. But in presence of the NAT charge, there appears another piece that resembles a magnetic force that it is proportional to this magnetic field B, and this magnetic field B is as always the curl of the vector potential, and this vector potential again is proportional to the NAT charge. So if you turn off the NAT charge, there is no magnetic part. And the interesting thing is that these particles follow this class of geodesics in here. And due to this, tau NAT geometry is usually thought of as a gravitational dione, in the sense that it has an electric and magnetic charges, masses in the gravitational context. And M is the electric mass, and N in this case is the magnetic mass of the solution. Okay. What about the asymptotic behavior of tau NAT? So the solution is neither asymptotically flat in the case where the ADS radius goes to infinity, neither is asymptotically ADS. And this has to do with the off-diagonal terms of the metric in this part that doesn't fall fast enough, and it is proportional to this cosinus theta and also proportional to the NAT charge. And this produces a kind of squashing of the sphere in the asymptotic region. However, it is worth mentioning that if you compute the Weil tensor, the Weil tensor goes to fall off fast enough as R goes to infinity. So at the best, this solution could be asymptotically locally flat in the case where the cosmological constant is 0, or asymptotically locally ADS in the case where the cosmological constant is present. So there are some things that Misner was studying in the 60s, and his analysis was done in choosing the following orthonormal frames. And then you can solve for the time differential in this case. And there are two pieces. The first one is the usual one that appears even for black holes, that tells us that there is an obstruction to foliation with hypersurfaces of constant time. This obstruction appears when this f is zeros, namely at the horizon. But in the case of tau naught, there appears an additional obstruction to foliation that comes from this piece, that it is proportional to the naught charge. And this obstruction to foliation appears when theta is equal to 0 or theta is equal to pi. And this is a sort of string-like singularity, similar to what happens in the case of the Dirac monopole, of the magnetic monopole, I mean. And there appears this Dirac string along one axis. So motivated by this, since in the case of the Dirac monopole, the position of the Dirac string is actually a gauge artifact, Misner tried the same thing in this geometry, and he chose a particular coordinate patch such that the position of the Misner string can be moved. So can be moved to the North Pole or to the South Pole, or even in the case where this ±1 is not in here, the Misner string is symmetrically distributed along the axis. This renders the position of the Misner string unobservable. However, the Misner string is there, as we are going to see next, because it has some properties, some physical properties like a non-trivial entropy. And the thing with this gauge choice in this case is that actually the space-time now has a Lorentzian time that it is periodic, and the period of this time is given by this a pi times the naught charge. And due to this, the tau naught geometry in Lorentzian signature has closed time-like curves. And because of this, the people used to study tau naught in the Euclidean sector, because usually it bears close resemblance with instantons in Yang-Mills theory, as I'm going to show next. But it is worth mentioning that some of there has been some new interest in leaving the Misner string as a physical thing, and this was done by Gerard Clement in 2015. And recently, it was considered also by Robert Mann and collaborators to compute the thermodynamic properties of the solution, leaving the Misner string as a physical entity. And they shown that the thermodynamic volume can be positive in this case, something that it is not guaranteed in the Euclidean case. So nevertheless, we will study the thermodynamic properties of tau naught in the Euclidean sector, since, as I was saying before, it bears close resemblance with instantons in Yang-Mills theory. So how does the Euclidean tau naught solution looks like? So it is given by this line element, and this line element can be obtained by doing simultaneously an analytic continuation of the Lorentzian time, and also an analytic continuation of the naught charge. And in this case, the metric is this one. But notice now that the area coordinate has a 0 at some point, actually at when r is equal to n. The area of the two spheres in here is 0, something that didn't happen in the Lorentzian case. And this is the metric function that solves the Einstein field equations in the Euclidean signature. How can we how can we do that the solution regular for the values of R that are allowed in this case? So there are two kinds of regularity conditions that we can use. The first one classifies this solution as the NUT, namely where f is evaluated at r equal to n, the metric function vanishes, and also we need to be sure that this metric is devoid of conical singularities, and in order to do that, we impose the following condition, where here beta is the period of the time coordinate, in this case, of the Euclidean time coordinate. And for Bolt, this solution is endowed with an Euclidean version of an horizon. This is located at r equal to rb. This is the Bolt radius. And again, if you would like to have a solution that is devoid of conical singularities, we need to impose this additional condition. Moreover, if we would like to have the Misner string to be an observable, the position of the Misner string unobservable, there should be a relation between the Bolt radius and the NUT charge that you can see down here. Additionally, this relation implies that both the NUT and the Bolt has the same period of the Euclidean time, and therefore they have the same temperature. So what does this condition implies? So the first condition here, the condition for the NUT, implies that this electric mass is related to the magnetic mass in the following way, as you can see here. And from now on, I will call this combination of N, G, and the ADS radius, I will call it the mass of the NUT. And for Bolt, on the other hand, we have that this condition down here fixes this electric mass in terms of the other quantities, the Bolt radius and the NUT charge in this way. So this is the mass of the Bolt. So I saw one hand raised. So if you would like to ask, please feel free. Milko, I saw your hand raised, or shall we leave it to the end? Okay, I do not see Milko anymore, so I will go ahead. So for the NUT, when we evaluate this electric mass in terms of the NUT charge and so on into the metric, and we compute the Weil tensor in this case, that is very interesting that for this solution, the Weil tensor is globally self-dual or anti-self-dual when the NUT charge is positive or negative respectively. And this is nice because this is similar to what happens with instantons in Yang-Mills theory. For those solutions, you also have that the gauge field strength is either dual or self-dual. And this is something similar to what happens here for the Weil tensor. And another thing that it is similar to instantons in Yang-Mills is that if you compute the Pontryagin index for this solution, it is actually different from zero. And recall that the Pontryagin index measured the difference between self-dual and anti-self-dual forms in the manifold. And so this non-vanishing Pontryagin index portrays somehow the non-trivial topology of this geometry. Okay, so to some extent, Euclidean tau NUT bears close resemblance with instantons in Yang-Mills theories. Okay, so what about the concept charge? Yeah,
may I ask something?
sure.
Sorry, I'm Tassos. Cristobal, I see when and the NAT charge is 0, the Pontryagin index is not 0 in your formula there. When I put n equals 0, this is
Yeah,
still not 0. What does this mean?
Yeah, I don't remember very well what happens in the case if you take the Euclidean Schwarzschild. What is the Pontryagin index of that? From here, it seems that taking n going to 0, you will end up with plus minus 2. But actually, I do not remember about the Pontryagin index of Euclidean Schwarzschild. In this case, if
Rodrigo, it should be 0. It should be 0. There is no Pontryagin is identically 0 for static black holes.
Yeah, yeah. So yeah, somehow at the level of the Pontryagin index, it seems that there is no continuous limit of n going to 0 in this case. So I believe that you should take this at the level of the line element and then compute the Pontryagin index. But that is a good question. I don't know what is happening in this case. Yeah, I will think about it, Tassos.
But
I don't know.
N is a real number or is an integer? I mean, to take the limit going to 0 should be a real number, but as an index, probably it is discrete or not. I don't know.
No, it is a continuous limit, but it's not a continuous limit, but it's a continuous parameter. N is a continuous parameter, but the limit is not continuous.
Okay.
To 0.
Mm-hmm. Yeah, thank you, Gaston. Yeah, I believe that you should take the limit. Yeah, it is not a continuous limit. So you need to first take n going to 0 here and then compute the Pontryagin index. In this case, I believe that at the level of the Pontryagin index, it is not continuous.
Sorry, Cristóbal, can I interrupt?
Sure.
I sorry to interrupt. I think in a 77 paper, Gravitational Instantons by Hawking, the Pontryagin was plus minus 2 for flat solutions. So I think it's a matter of the starting point, right? Because really what matters is the difference with respect to the non-instantonic vacuum when you add instantonic numbers. And I think the normalization we used was the one for such that it retrieves Hawking results as you send. For instance, if you send L to infinity, this gives you plus or minus 2, which is the result of Hawking for NAT flat.
Exactly.
Ricci flat NAT. So it's true that when you send n to 0, though, and keep n finite, you get plus or minus 2. That seems to not be the case for Schwarzschild. So there, I don't know. But at least for the flat limit, I'm sure that as you send L to infinity, you get plus or minus 2 consistently with the 77 Hawking paper.
Yeah, thank you, Luca. Yeah, I agree with that. But actually, yeah, it is interesting that the case here with n going to 0, it seems to be a not continuous limit. So yeah, I will think about it. Okay, so what about the charges of this solution? So in order to compute the charges, one can use the Netherworld formalism. And so for those of you that are not familiar with this, I prepare a super brief review. So to compute charges in a gravitational theory, there are different methods, but the one given by Nether and Wald is the following. So if you start from an action principle, like here, this is an action principle that only depends on the metric, and such that the Lagrangian depends functionally on the metric and derivatives thereof through the Riemann tensor in order for the theory to be invariant under diffeomorphisms and local Lorentz transformations. So if you start from here and perform stationary variations, you end up with the field equations plus a boundary term. Okay, so the field equations in a quite generical way can be written in the as follows here. So and also the boundary term is given by this expression, where this E tensor is the functional derivative of your Lagrangian with respect to the Riemann tensor, and this tensor this E tensor plays an important role in the netherworld formalism. So if you compute E, you are kind of almost done. You have to evaluate it. You have to evaluate some things, but this piece is really important now. So if your theory is diffeomorphism invariant, there appears a conservation law. So you can write the boundary term plus something that appears from the variation of the Lagrangian as a current. This is, let's say, the nether current. And this is proportional to the field equations of your theory. This is the explicit form of the nether current. But on shell, for any solution that satisfy the field equations, you have here something like a conservation law. So your covariant divergence of your nether current is actually 0. And therefore, the Poincaré lemma, in turn, implies that locally you can write the nether current as the covariant divergence of a 2 form, that from here on I will call this 2 form the nether prepotential, and explicitly is given by this equation where this chi is a Killing vector of our metric. Now, how can we compute some the nether charge of the solution? Then you need to integrate the nether prepotential in a codimension 2 hypersurface. So this is the formula that you need to compute. And in this case, I just redefine Q, which is a 2 form. I defined the dual of the 2 form as a d-2 form, this capital Q. And you integrate this in a codimension 2 hypersurface, and then you end up with the nether charge. The nice thing that Wold shown in their perhaps most famous paper, besides his book about general relativity, is that if you evaluate the nether charge at the horizon of a black hole, that gives you the entropy of the black hole. And essentially, if you do the same, for instance, in any other hypersurface that obstruct the foliation of the space with hypersurfaces of constant time, then you will get additional contributions to the entropy of your solution. So this is the case, for instance, for tau NAT. As I was mentioning before, there appears different obstruction to foliation in this case coming from the Misner string. And usually for black holes, you have that these are the components of the dual of the nether prepotential, and you integrate this at the horizon, and then you end up with the entropy of the solution. But now we have an additional contribution coming from the Misner string. As you can see here, this is proportional to the NAT charge, and you have to integrate this dual nether prepotential at the horizon and along the Misner string. And so this is the thing. Here is the contribution to the entropy coming from the horizon, but additionally you have additional contributions coming from the Misner string. And these are the two integrals that you have in here. And for asymptotically locally flat spacetimes, the entropy was computed through the Waltz formula in this article by Garfinkel and Mann in this classical and quantum gravity paper. And by using Euclidean methods was done by Robert Mann and also by Empar and Johnson Myers and other people after them. by introducing counter terms, which are covariant counter terms, but covariant at the boundary. The thing is the following. If you would like to compute the entropy of tau naught, in particular the contribution coming from the Misner string, using the Netherworld formalism in asymptotically locally ADS spacetimes, these two pieces are divergent. You don't have any problem with this because the radius is finite at the horizon, but here there appears an integration from the bolt radius to infinity, and these two contributions of the Misner string becomes infinite. So we need a prescription to render this result finite in this scheme, similar to what happens in the case of the Euclidean action method. And therefore, we found that an interesting choice is to introduce topological terms into the action such that these two terms actually become finite. So this is perhaps the main message of this talk, of this work, and this is the topological renormalization and the Misner string entropy. So there was a super nice paper by Aros, Contreras, Rodrigo, who is also here in the audience, Ricardo Troncoso, and Jorge Zanelli in these physical review letters. They shown in this article that you can actually renormalize nether charges in asymptotically ADS spacetimes by introducing the Gauss-Bonnet term into your action. And in this case, the Gauss-Bonnet is a boundary term plus the Euler characteristic. And it turns out that a proper choice of this Gauss-Bonnet coupling renders some of the charges and other quantities finite. So I would like to explain this a little better in the following. So the Gauss-Bonnet is this invariant, as you can see here. It doesn't affect the bulk dynamics of the metric, and therefore the Einstein field equations remain the same. But this term modifies the E tensor in the following way, and therefore it will modify the definition of conserved charges. And so if we start from here, and if we would like to solve the Einstein field equations, we solve it by Einstein spaces, as you can see here, where the cosmological constant has been fixed in terms of the ADS radius. And then for these spaces, the field equations are solved. And now the nether prepotential can be written in the following way, as you can see here. Now, in asymptotically ADS spacetimes, the Weil tensor has the proper fall-off as R goes to infinity. Asymptotically, the Weil tensor goes to 0 in asymptotically locally ADS spaces. But now we have here a piece that is proportional to antisymmetrized deltas. So this will be a problem in the asymptotic limit, but the role of the Gauss-Bonnet term is that you can fix from here alpha such that this term is absent. And in particular, if you choose alpha equal to the ADS radius square over 4, the action can be written as the one of McDowell-Mansouri on shell, and the charges become finite. And therefore, we computed the entropy using this particular choice of the Gauss-Bonnet coupling. And using the Waltz formula, we end up with a finite result for the entropy. In particular, the problematic thing was the Misner thing in this case. And then we managed to produce a finite entropy using the Waltz formula by introducing the Gauss-Bonnet term. This is the result that we got. And also we computed the Euclidean on-shell action that it is given by this expression. And as a matter of cross-check, we computed the entropy using Euclidean methods, and it matches the result of the entropy using the Waltz formula. And finally, you can compute also the mass of the solution, and the mass of the solution is this, and it matches the mass that I showed you some slides before, the mass that appears as demanding regularity conditions of for the metric at the volt. Yeah, I heard some question over there.
Cristóbal, here.
Yeah. Christian.
So if you take the limit again here, it doesn't make so much sense, right? For the entropy. When the limit when n is equal to 0, close to 0.
Yeah, actually, we were trying to play with that, with n going to 0, and it seems that there is no continuous limit at the level of the entropy in this case. We were also playing the game of going from the volt to the NAT case, and we didn't find a continuous limit either. So they didn't seem to match in this sense. So the best thing that we can do in the case of to compare volt and NAT is to start from the beginning from the metric and then evaluate the entropy from the scratch, I mean.
I see.
We checked that this.
Sorry, sorry, Cristóbal, it's Tassos again.
Tassos, please.
Yes, one thought that I have is that actually what you are doing is you are subtracting the entropy of the Schwarzschild. That is why you are finding, you know, everything to be 0 when n goes to 0, and also in the case of the Pontryagin index, I don't know, maybe there is a way that you are introducing some non-trivial topology in your theory such that you start from a state whose entropy is 0 when n is 0, which is not the Schwarzschild black hole. The Schwarzschild black hole has non-zero entropy and also 0 Pontryagin index. So you start from somehow a state which I would say it is a self-dual state which has non-zero Pontryagin index because it's topological, but also has 0 entropy when n goes to 0. That's one, you know, thought that I have that maybe is consistent with what you are doing.
Yeah, exactly. So thank you very much, Tassos. I do agree with your interpretation. In fact, yeah, it seems that there is at the level of the thermodynamic quantities and also the Pontryagin index. I would say that yes, you have to start because you are choosing a state that it is that it has non-trivial topology, and in that sense, I would say that you should start from n equal to 0 from really from the scratch. So yeah, thank you, Tassos, and thank you, Christian, for your questions. I was also wanted to say that these thermodynamic quantities satisfy the first law of thermodynamics, and they also satisfy the Gibbs relation down here. So the other thing that we were wondering was about what is the role of other topological invariant that can be added to into this picture. In particular, what happened with the Pontryagin into the game. And so we also included the Pontryagin here with a parameter, this theta parameter in front. The Pontryagin is, so the Pontryagin is this is the definition. And the thing is the following. So regularity of charges and also regularity of the Euclidean action doesn't theta. In fact, only by choosing alpha in the following way, the regularity of your Euclidean action and of your charges is completely guaranteed. So we need another criteria to fix theta in this case. And the criteria that Rodrigo and Oliveira shown in this, found in this paper, and also with other collaborators in this other one, was to fix theta such that when you evaluate the action and the other quantities at a self-dual or anti-self-dual solution, the Euclidean on-shell action vanishes identically, as well as the net prepotential, and therefore all the conserved charges. And this is similar to what happens with instantons. So you have as a ground state, which is of course with a non-trivial topology. But in this case, for this, for a self-dual background, in this case, the Euclidean action becomes identically zero, as well as the charges in here. And you can see this directly from the form of the action. So if this, for a self-dual or anti-self-dual solutions, this is essentially zero. So we can compute the thermodynamic quantities in the case where the Pontryagin is added, and we found that the entropy, Euclidean action, and thermodynamic mass are given by the following expressions. But the thing is, you can see that, for instance, in the case of the thermodynamic mass, this is the difference between the mass of the bolt and the mass of the nut. And in fact, as you can see here, the Euclidean action is zero for the nut. So this seems that the Pontryagin term is setting as a background reference the tau nut solution, and then you are computing the thermodynamic quantities with respect to the nut when the Pontryagin is included. And so it is direct to see that in the case of the mass of the nut, when you replace here the nut, the thermodynamic mass is zero, and also all the other quantities. And yes, so that's the thing. So including the Pontryagin fixes the tau nut ADS solution as the reference background. And finally, there is another way to compute the energy or the mass of the solution. And this can be done by computing the boundary stress tensor in ADS. And in this case, the usual Bala-Subramanian-Krauss receives contribution coming from the Pontryagin invariant. And this is translated into the Cotton tensor in the boundary stress tensor. So the boundary stress tensor is the Bala-Subramanian-Krauss stress tensor and the Cotton tensor in here. And this is the definition of the Cotton tensor in terms of the boundary metric. And it is interesting that for tau nut and bolt, the Bala-Subramanian-Krauss tensor is related actually to the Cotton tensor through this relation in here. This is for arbitrary value of the electric mass. And if you introduce here the value for the nut, then these two terms in here cancels each other, and then the boundary stress tensor is identically zero, which is consistent with saying that in this case, the Euclidean action and the net prepotential are identically zero for the nut. It happens the same here. So the boundary stress tensor, when you include the Pontryagin density and evaluated this boundary stress tensor at the nut, then the boundary stress tensor is identically zero. So this is what I have to say. So my conclusions are that in the tau nut solution can be thought of as a similar to as a gravitational analog of instantons in Yang-Mills theory. Moreover, since this is a gravitational analog of a dion, we have a piece that it is proportional to an analog to a magnetic monopole. And therefore, there appears this string-like singularity called the Misner string, which is the gravitational analog of the Dirac string. And the thing is that the Misner string has non-vanishing entropy. This has been computed in asymptotically locally flat spacetimes. But in the case of ADS, the contribution of the Misner string is divergent, and therefore we need a renormalization prescription. We studied the case by included topological terms like the Gauss-Bonnet, and by choosing a particular value for the coupling constant. This renders the Misner string entropy finite. And finally, including the Chern-Pontryagin invariant doesn't introduce any other restriction about regularity, and we need another criteria to fix the parameter in front of the Pontryagin. And this can be done by demanding that all charges and Euclidean action becomes zero evaluated at a self-dual or anti-self-dual solutions, and therefore it fixes the tau-NAT solutions the tau-NAT solution as a referent background. And finally, so this is the last part of my talk, I would like to give an advertisement. My colleagues and I are super happy because we recently got approved our master in physical science. We will start the next year, starting on March. And so we have here the period to apply for this program. So we are looking forward, bachelor students, to apply to this master program. And if you have any other question, just write us, and we can talk about it and give you some guidance and to tell you about what would be the program the next year. So this is all that I have to say, and thank you very much, guys.
Thank you very much, Cristóbal. Thank you. Exactly, you can put your microphones. It's the last seminar of the year, so we can make some noise. So also, before passing to the question session, also we are happy because we got last week a very good news also that Ignacio Raya got a project to join our group during next year. So we have Ignacio in the audience. So we also use this moment to welcome you, Ignacio.
Thank you very much, Nelson. Thank you for your
Felicidades.
work. Muchas gracias. Yeah, I'm very happy to be part of the UNAP team now. I'm very happy, very excited. Yes, it is a great time because the university is growing at a rapid pace, so it is the perfect time to start new things with a lot of with a lot of force, with a lot of input.
Yeah. Super. Thank you very much, Ignacio. Thanks. So the audience, you can please ask your questions. Feel free to.
I have a question.
Yes, please.
So, Cristóbal, when you only include the Gauss-Bonnet term, you also shield the background as well?
Not really. This is sort of a background independent scheme. And so different to what Hawking and Page did in their 90s paper, they used this subtraction method to compute the entropy of tau-NAT in ADS. But in this case, you don't need to subtract any background, but you have to pay the price that you need to fix the coupling in front of the Gauss-Bonnet. And yeah, this is the thing that you need to do, and that is enough to render the entropy and all the conserved charges finite.
Because I thought that happened something similar, that that when you add the Chern-Simon term, the second term after the Gauss-Bonnet, when you add the other term, which one is it?
Yeah, the Montriagin one, exactly.
Okay. When you add the Montriagin term, you say that you shift the background.
Yeah, then you shift the background. In that case, the background, in that case, all your charges and thermodynamic quantities are measured with respect to the tau naught, similar to what Hawking, Page, and Hunter did. But in this case, you don't need to subtract the background. So including the Montriagin, just fix tau naught as the background. That's the thing.
Okay, and doesn't happen the same when you only add the Gauss-Bonnet term.
Yeah, I don't think so. Yeah. So yeah, you get the, obviously you can subtract in this case the entropy of nut of bolt minus the nut, and you can get the same result. But yeah, I believe that it doesn't fix the background in that case.
Can I ask a follow-up, or maybe just make a comment before asking a question? Actually, the comment I wanted to make is also related to what Tasso was saying during the talk. We have commented in two steps, I would say, upon the fact that the n goes to zero limit may be something tricky. Actually, what is going on in that limit is that since we have required the absence of conical singularities at the nut or the bolt horizon, when you can see immediately that when you take the limit n to zero, you are actually sending to zero also the electric part of the mass. So actually you ended up in ADS rather than ending up in Schwarzschild. And that's why the entropy, you can check at the entropy for nut, ADS nut, as you send n to zero, it becomes a constant. And of course it does not depend by the electric part. So you don't reproduce the usual Hawking area law because there's no electric mass in it. That's what is happening. It's going to zero as well as the nut.
But I think generally the Pontryagin would be proportional to the mass times the nut times the other stuff. So times some other stuff. So it would go to zero with n as well as m. If I don't tune to the nut case.
You mean the Chern-Pontryagin index? You mean?
Yeah.
Yeah. Yeah. No, there I don't have a comment about the limit. To be fair, what I have a comment was about the entropy itself, because when you see the entropy for nut now, you can think that sending n to zero you should find the Schwarzschild, but that's naive, because what is going on is that you are killing also the electric part of the mass.
So can I comment on that again?
Yeah, please.
That's rather confusing, right? Because you might have thought that the proper notion of entropy in any geometry that has a mass would know about that. And if this is some sort of subtracted version of entropy, how do I think about that physically? I guess that was a question rather than a comment. Sorry.
So what is the question again, Prof? Is it?
Well, I guess the question is that if I'm supposed to think about the finite entropy that you compute as some subtracted version, how do I think about that physically? The general solution has a mass, and so I would have thought that that was an important parameter, but I thought I was hearing that in fact because you're subtracting off something important there.
So in the case where only the Gauss-Bonnet was included, or
for example, yeah.
Yeah, so in that case, we were able to reproduce modulo a constant, the same result as, for instance, Empar and Johnson-Myers, and also Hawking, but they were doing this method of background subtraction in that case.
Yeah.
So yeah, in our case, for the bolt, for instance, we have the constant that it is. We have only a constant of difference in that case, and I believe that has to do with the method that we are using here. So since the Gauss-Bonnet is the Euler characteristic plus the exterior derivative of the Chern form, in that case, I would say that the difference of the constant comes from the Euler characteristic in this case. But the result is I didn't mention that, but the result is the same as the results, the well-known results in the literature. So
can I make a question just to
I think I misunderstood.
So here there are two results, if you want, one without adding the Pontryagin and one adding the Pontryagin. So there are two topological invariants. We all know that if we add a topological invariance, entropy can change, of course, because the evaluation of the action can change. So if we don't add the Pontryagin at all, and we just add the Gauss-Bonnet term with the coefficient that makes the variational principle well posed and the charge finite, which fixes totally the coefficient, so the results agrees with the one that everyone's computed so far. For instance, Clifford, Johnson, or Emparano and company, up to an additional constant piece, which is actually not a problem, but actually better, because they have, probably you remember, they have a negative entropy problem in ADS, which is for some particular values, entropy gets negative, as Clifford Johnson mentioned in his paper. We don't have this because of the addition of this constant. But up to this constant, namely everything that relates to variation, like first principle and so on, we totally agree with them. But when we add the Pontryagin, then the result changes. And this is the one that changed. So you would say probably don't add the Pontryagin, which is probably the right thing to do. But that's the summary. So if we don't add the Pontryagin, we just put the Gauss-Bonnet term, then we totally agree that our result reproduces those that everyone has computed with different methods.
I see. Okay.
Can I add something to that, Gaston? Just in line with that is that what the Gauss-Bonnet is doing is not to adding or subtracting a background that depends by the electric mass. This is a completely independent phenomenon. The fact that the electric mass does not appear in the equation is that it is actually hidden in the nut charge, in the magnetic part, because they are related in this solution. It's not that the electric mass does not appear or in the limit does not show up. The fact that the limit not goes to zero imply that the entropy becomes a constant is because you're taking this limit in the dion as you take also the electric mass to zero at the same time. So you end up with just an empty constant for the entropy.
Which means it's a constrained system. You don't have freely electric and magnetic mass. They're the same.
Yes, and for bolt is even more complicated actually, as Cristóbal mentioned in the talk. When you send the bolt radius to the nut radius, is definitely a tricky process, right? So
yeah, because you are restricting yourself to the self-dual solutions. I mean, you are taking the limit within the family of self-dual solutions, because you set the action in such a way that the actions become zero, identically zero for globally self-dual solutions when you add the Pontryagin. I mean, I wanted to say something. This is it took us long to realize of a very simple fact, that it was the addition of the Gauss-Bonnet. The addition of Gauss-Bonnet turned the action in a quadratic form, in this McDowell-Mansouri form, is actually almost a gauge theory. It's almost F squared. So it's identically zero for global ADS. So if you add the Gauss-Bonnet term, the nether wall charges become proportional to the Weil tensor. So the nether wall charges are identically zero for global ADS. So if you evaluate the nether world chart at the horizon, it will be the entropy that is identically zero. So it's the minimal consistency check for the vacuum state of the theory. For global ADS, everything becomes zero when you have the Gauss-Bonnet, the action, the mass, and the entropy. So replicating this idea is that you have the Pontryagin term, and now you change the vacuum state from global ADS to something that is globally self-dual. So the action becomes zero for globally self-dual, the entropy becomes zero for globally self-dual, and also the mass.
Yeah, thank you, Rodrigo.
So it means basically that you actually don't have a continuous limit towards the Schwarzschild black hole. This is what you are trying to do. You are
yeah, you're in a different vacuum somehow.
You are in a different vacuum.
Sorry, but let me precise. In what sense there is no limit, continuous limit? The metric is certainly continuous. There are some things that are continuous. But the point is that what happened with the Pontryagin? For instance, if you check the paper of Hawking in the 1977, not the one with Gibbons 1 year after, the one of he just computed asymptotically locally flat space-time. The Pontryagin for tau nut. In that case, it's 2 or minus 2, depending on the sign of n. It's not n or something like that. It's 2 or minus 2. Of course, in the limit going to 0, and it will be just a space that is parity even, and then it will be 0. So this limit is not continuous. So the value of the limit of the Pontryagin is not continuous, but it's not that the thing is not continuous. The mass is continuous, the entropy is continuous, the metric is continuous, so everything is continuous. Just the value of the topological invariant is not continuous, just because a rapid way of saying this is that it doesn't matter how small n s is, the solution will be parity odd, and if you compute the Pontryagin, it's different from 0. So, and it's constant. I mean, you can take it. It's like if you want, it's 2 times n divided by modulo of n or something like that. So in the case n going to 0, you have to recompute it. And this flat space is 0.
Yeah.
But this is what is not continuous. The rest is everything is continuous and everything is nice.
Exactly. I think that the thing with this continuous limit has to do with the identification of the electric mass and the magnetic mass. After you identify that, then I would say that there is no continuous limit to Schwarzschild of n going to 0. But before that, you can take safely the limit because they are not related. But after you identify them by saying that this is the nut or this is the bolt, then I would say that there is no continuous limit, at least at the level of the thermodynamic quantities. And perhaps this also happened in the case of the Pontryagin index, because in order to get the plus or the minus 2 that Gaston was saying, you have to identify that m is related to the nut charge, and therefore you don't have there this limit, this smooth limit of n going to 0. I would say that that could be the thing here.
If I may, also in that limit, what happens is that there's a topology change. So there is a bundle that becomes trivial. So you would have to recompute the topological invariant because the topology changed.
Yeah, thank you, Danny. Yeah, I agree. Mm-hmm.
The story with a kind of a generalization of the Hawking page transition case, which means you pair the entropy with the entropy of the global ADS, and whether there is a point where, I don't know, is there a phase transition point there for some value of the nut charge? I think people have studied that in the past, but I don't remember.
There is this paper of Clifford Johnson about the phase transitions, I think. But this is something that I am interested in. I would like to take a look on that. But I believe that Clifford, even in the extended phase space, where the cosmological constant was treated as a pressure, they were studying phase transition in that case, and also in the case where the cosmological constant is only a parameter. So yeah, I think that the reference to take a look at is one of Clifford Johnson.
Any other comments? It's quite nice that it was more than like a discussion session than question session. So this is quite positive. So please feel free to take a...
Let me try to answer or ask another question. So one of the things that Tassos and I emphasized in our recent paper was, and this is really from the Lorentzian table point of view, what was the invisibility versus physicality of the Misner string. And in recent thermodynamic discussions, people have advocated the physicality of the string, and that has an important effect on the thermodynamics, right? That there's, in particular, there's a thermodynamic partner of the nut charge. Do you have any comment about that in your context, or?
Yeah, that's a very interesting question, Rob. Actually, I saw this article the last year of Robert Mann, and they were doing exactly what you are saying. So let us stay in the Lorentzian case and leave the Misner string as a physical thing, and compute the thermodynamic quantities in that case. And in our case, we demand that the Misner string is, the position of the Misner string is unobservable. So certainly it's something that we can, with the same prescription, we can take a look at. In the case of the Lorentzian case, we haven't done yet. We haven't done that yet. And yeah, it is something that we can do. To see what is the impact of the Misner string as a physical thing, and to see what happened in the case where the topological terms are included. Yeah. So, yeah.
Can I make an incomplete comment? Because I totally agree with what Cristóbal said, and indeed we didn't add as not only Robert Mann but also Jenny Trajan and David Castro like to do, of putting this a chemical potential associated to charges, or even what Clifford Johnson does of putting the volume analog of the. But we have a incomplete result in that direction, which is what we did is the following. Since we are getting a contribution to the entropy coming from the string, we ask ourselves, okay, how it changes if we use different patches. For instance, let's consider the integration, having the two strings, or which contribute non-trivially to the entropy, or let's change the thing and use the different patches in which only one string is there and the other one is absent. Because since the integral on the string was contributing non-trivially, it cannot depend if it is physical on what patch we use. And you can see that our result is invariant. Namely, if you, for instance, consider the two strings, you get the same result as if you don't consider one and you consider the patch in which there is only one. In that case, the only one that is present contributes twice the previous one. So we observe that indeed there is invariance. So at least, that's why I say it's incomplete. It's not satisfactory, my comment, but at least it's consistent in the sense that we see that with different patches, it's invariant what we suppose is a physical result, which is the contribution of the Misner string to entropy.
Sure, if the string is invisible, then you can have any number of strings you like and you can put them anywhere you like. It's not going to matter. Yeah. And it's good that that you see that explicitly, but it's a completely different story if you take the strings to be physical.
Exactly.
Then the number and the location matter, presumably.
Yeah, we haven't taken into account the case where the string is physical. So that's certainly something, an extension that we can look at. So yeah, it's interesting. Thank you, Rob.
May I add small question.
Sure.
From the ignorance, of course, because, well, I don't know about this kind of more complicated solutions with these strings, but about these regularization procedures. For example, as Rodrigo mentioned, when you have this McDowell-Mansouri action, this action is already finite and gives you finite charges in the simple case of pure gravity, let's say. So it gives you finite charges, and we know that somehow you need to have a cosmological constant different than 0. And if you want to calculate something with cosmological constant equal to 0, usually in pure gravity, the realization procedure, in order to ensure the finiteness, in order to have a action and charges finite, usually you apply there a subtraction. You have to subtract a background to obtain these finite charges. So my question is, in this case, you mentioned that there was a calculation made before using a background subtraction, and this procedure you have, it is background independent. But it is also a necessary condition to have cosmological constant different than 0?
To get the charges finite, do you mean? Or
so the results you have, because somehow adding these topological terms somehow has some effect in order to have a regularized charges.
Mm-hmm.
But in the case you have a cosmological constant equal to 0, usually you apply a background subtraction instead of adding a topological term. So my question is, you mentioned that the same result it was calculated before by Hawking in some.
Yeah, but that was in ADS. So they
it was in ADS.
Yeah, it was in ADS. They did the calculation of the entropy of tau naught by performing the subtraction of tau naught. So there was tau volt minus naught. Since the solution is not asymptotically ADS, it has their own asymptotic behavior. Then you need to you cannot subtract ADS in this case. And the way around that they used was to use tau naught as a background, and they subtracted the naught to the volt. So their solution for the volt in ADS is subtracting volt minus the naught, and they obtained the result in that way.
Yeah. Okay. So it was also background subtraction, also in the case of ADS, what the Hawkins made.
Yeah, exactly. Mm-hmm. And in flat space, if I remember correctly, this article of Garfinkel and Mann, they computed the entropy following the Waltz formula, and they were able even to reproduce the case of Hawking by subtracting. They computed for both, for the volt and for the naught. And the first cross-check was to see whether this result by subtracting volt and naught coincides with the case of Hawking, Hunter, and Page, and actually it does.
Okay. So the same result can be applied for a case with cosmological constant equal to 0. Can be applied.
Yeah, I think if you start from the nether charge and compute it for asymptotically flat cases, in that case you don't need to subtract any background.
Perfect. And the procedure is the same. You have your topological terms in the action, and
actually, in principle, you don't need to add any topological terms, because the result in that case, if I remember correctly, is finite. At least using the prescription of Wald, the result is finite in that case. The problem comes from ADS, because remember the entropy in the case of for black holes only depends. You integrate over the horizon. And when you integrate, in the case of tau naught, in asymptotically locally flat spacetime through the string, along the string, I mean, then the charges are finite. the thing is, in ADS, the contribution along the string is actually infinite. So then you need to include something to regularize your charges.
Thank you. So any other comments? So if not, we thank you, Cristóbal, for this nice talk. So
thank you, guys,
and thank you very much, everybody, for being here. It's a pleasure to see you and to meet many of you, even if it is virtually. So
we will come back.
We'll come back. Yes,
Congratulations, guys, Cristóbal. Nice seeing you. Hope to see you soon.
Nice to see you, Tassos. We will see each other again sooner or later.
Yeah, very nice to see you, Rodrigo. I hope to see you soon. Very
Thank you.
soon, really.
Yeah, definitely. I have to travel.
You guys.
Thank you.
Thank
guys.
you.
Yeah, it's super nice to see you and meet you, Tassos, Rob, and all the other people here in the audience. And thank you very much for being here. And let us hope to see you soon in person and not virtually. So thank you, guys.
Thank you. Thanks a lot.
Thank you.
Ciao, ciao.
Bye, guys.
Ciao, ciao, Rob.
Goodbye.